pilot. All right.
Hello, everybody.
Good morning.
Good morning. I'm Sid Nagel.
I'm Heinrich Jaeger. Welcome to Physics with a Bang.
Are you ready for a bang? Yeah. Okay, let's give them a bang.
All right.
Are you ready? Here we go. Okay, so this may be a little loud, so keep your fingers in your ears ready to...
Wait a second. Are we ready?
Are you ready? Oh, but this is not ready. Okay, so now, here we go. 1, 2. Whoa! Okay. So,
all right.
You want to hear another bang?
Yes.
Okay, here we go.
Well, that was nice and loud, wasn't it? And one of the wonderful things we can do here is, because we have some operators of a very fast camera, we can play this back to you in slow motion. So let's see what we just experienced. I'll make it big. All right, so there is the light. And see what happens first. Before any explosion, the balloon peels back, and now the explosion starts. See that?
And so these are our camera operators. So this is Severine Atis, Melody Lynn. And how fast did you film that? 4,000 frames per second, and you played it back at? 30, so a factor of 10. Okay, good, we can do that. Okay, so now we need to get a volunteer from the audience.
I need a volunteer.
Okay, so here we have a volunteer.
Whoa.
So can you help me come down? You're going to have to help Heinrich over here.
All right, come a little closer.
Come over here.
And now, is it okay if I pick you up, because you need to turn this for me, okay? Oh, you can do that. Okay, there you go. Now look, as you turn that, we turn on a light bulb here. Come on, you can turn this up.
Turn on a light bulb there, and we're going to try and light something up over on this side of the auditorium.
And a little bit more. Yeah, see that? And see how you can light it up.
It's getting brighter over there.
Can you do a little bit
And let's
more?
see if we can set this thing on fire.
Oh, keep going, keep going.
Keep going. Oh.
Whoa.
Oh, there. Look. Whoa. Thank you very much. Let's give her a hand.
Thank you. That was wonderful.
Okay, so one of the things that we like to do in this show is have a little things about transportation, for example, and so we ask, how do airplanes fly? And so one of the things that keeps airplanes aloft is this thing called Bernoulli's principle. And so if I blow over the sheet of paper, I'm blowing over it, and you would think the paper is going to get out of the way. That's the whole idea of blowing on something. But let's look what actually happens.
Sit more. There.
So as I blow, it actually comes into the flow rather than away from the flow.
That was
that
great.
neat?
That was wonderful.
Was that wonderful?
But let's make it a little bit more
industrial style?
Industrial style.
Okay, industrial style. We will do it industrial style. Okay, so here we have a blower, and this is a sheet of paper hanging from the table, and the blower is above the sheet of paper. So now we turn this on, and it goes up. Whoa!
That was great.
That was better, okay. What else could we do, Heinrich?
I found something.
Oh, what is that? Okay. Let's see what we can do with that.
He blows over. Okay. Well, that was pretty much fun, wasn't it? Now, the very same effect, this Bernoulli effect, that also works if we have a spinning object. So what I'm going to do is I'm making an object that spins and moves really fast at the same time by wrapping this rubber band over two cups that we stuck together.
So that's kind of like this, where this was air rushing over something. Here, you're pushing something through the air.
Right. And you know what? Since this turns, the air on the top and the bottom of this thing will go at a different speed. And what we're going to see is now a slingshot, right? Oh! That was not exactly what we had in mind.
Okay, well, what did we have in mind?
We had in mind a slightly different effect. And let me try that now. Let me try this now.
Whoa. So that's kind of like a curveball.
Yes, that is a curveball.
So we're getting ready for spring already.
So if that's a curveball, then let's try a curveball. So instead of shooting that up in the air, I'll try to shoot it around Sid, but let me do that from this side.
Okay, I dare you, Heinrich.
So I'll shoot it now at my colleague here and see if I can get around him. Oh! And I didn't even break this thing, so.
Okay, so now how many of you take music lessons, play musical instrument? Oh, a lot of you play musical instruments. That's great. And so what do you need to do if you play a musical instrument? Well, practice is good. Practice, practice. And how do you practice? Well, you have to get the notes right. And if you don't get the notes right, it doesn't sound so good. But the other thing you have to do is you have to get the thing in the right rhythm, right? If you don't have rhythm, the music just doesn't do it for you, right? And so what does your music teacher tell you to do? Well, they say, get yourself a metronome, and the metronome will give you a steady beat, and then you practice according to that steady beat and see what you get. And so here is a metronome, and we'll see what it sounds like. And so here is a metronome. That's a nice metronome. It's a steady beat. But if one metronome is good...
Well, how about two?
Two should be better, right? So let's do two. And if two is good...
Three, four.
4, 5. So this should really keep you on the beat, right? Oh my goodness, I can't tell anything now. I mean, it's just a mess. And so how am I going to get it so that all these metronomes go together? And so what we're going to do is we're just going to take these soda cans and take these metronomes, which are on this sheet, and just move them up. And there we have it. So all we had to do was put the cans on these, put the metronomes on these cans so that then they got to talk to one another, and if they get to talk to one another, things are better. And so this is a rule for life.
So since we had a musical theme here, and since it's the holidays, let's turn down the lights a little bit and turn on some other lights.
Okay, so this is very festive.
So what do we have here? We have a tube with gas flowing in. This is just like your burner if you have a gas stove at home. And sit here.
Okay, there
lit
we
all
go.
those, and now what do we do?
And so what we have here is, so this is a tube with holes in it, and so the gas is coming out like burners at home, as Heinrich said. And what we want to do is we want to show you that sound is actually a wave. And so what we're going to do is, with this tube, we're going to put a speaker on it one side, which is one tone, and then you'll see this, these flames come out at different heights. So let's watch that. And so because the pressure in the wave is different at different points, you can see what the wavelength of this sound was because you see the oscillation in the shape of this. So let's see it again. Okay.
This is where you're going to sing now.
Voila.
All right. That was beautiful, wasn't it? And it was quiet and festive. And now we're going to see what else we can do with sound. We crank it up a notch or two or three, and we make it so loud that the sound becomes destructive. And what do we have in mind? We have in mind creating sound that is loud enough to break a wine glass. So what you'll see in a few minutes, we'll put it on the big screen, is a wine glass that's inside here, this little box, and there are two speakers below it that will generate a tremendous amount of sound. And so Andrew here is going to set that up.
And you'll see on the screen the picture of this as it's going on, and you should concentrate on the rim of the glass as this thing gets put into focus. And this will be somewhat loud, and so I would encourage you to use your fingers when it goes. We'll tell you when to do
Don't
it.
worry,
But
we'll
I mean,
tell you. So by the way, if there's some people in the back, there are still seats here. If you can come down, there's some seats over here.
On
There's
the
some
sides
seats there.
and
Just
the
come
middle.
on down here and find a seat.
Okay, so there is the glass. There is the rim of the glass in front.
Right? And you see the two speakers underneath these black things, and they will send out a sound wave like we just saw, but this one will be potentially loud.
Okay, and so this is where when we go, this is where you should put your...
But wait 1 second here, the people still sitting down.
Okay, so we'll wait for people to get seated. Do you want to come on down? There's some seats here.
All right.
Okay.
So now, you want to put the fingers in your ears.
So you can see it vibrating. Whoa!
So what Severine and Melody are now doing, they're finding the right spot, and you see here in slow motion what really happened. So the nice thing about this is these are research grade cameras that we use in our research, also in our labs. And that makes this particularly nice because you see things that are really hidden in time that you couldn't catch with your normal vision because they are way too fast.
Okay, so now we're going to talk a little bit about gases. And what I'm going to do now is I'm going to pour some of this, a little bit of flammable alcohol into this big water container. And I'm going to try and coat the inside of this with the liquid. Now, this is going to take a little bit of time, so I have to tell you a story while I'm doing this so you're not completely bored. And so the idea about this was that there's a nice YouTube video of someone in the middle of winter getting out of a car at to fill their tank with gas, and it was cold, so they put the nozzle into their gas tank, and once it got into the gas tank, they went back into their car, and they closed the door until things got warmer, and then when this thing finally filled up, they got out of their car, and they went to pick up the gas handle, and they touched the gas handle, and the whole thing burst into flames. And so the car just went poof into smoke. And so what happened was, well, this person had gotten into the car, and their clothes had rubbed against the seat of the car, and there was a little bit of static electricity on their coat, and then when they went to touch the nozzle, it burst into flame. And so this, at the end, no one was hurt except the car. The car was no longer there, and this was captured by their cameras that were just looking at making sure people were paying at the gas station. And so this got onto YouTube. And so what we want to do is want to show you that this is actually quite a dangerous thing that you can get if you aren't careful about flammable gases and flames. And so what we're going to try and show you now is what happens where I have flammable gas that was inside this container, and I'm going to now just put a light on this and see what happens. Are you ready? You're ready. Okay, so let's see what this goes. Okay. Okay, so
Wow, that was nice,
that's
wasn't it?
what can happen if you're not careful with flammable gas, and that would certainly be rather destructive.
So, you want to play that back now, or what should we do?
Let's see if can we.
Okay. So see how it starts at the very top and then moves into the container.
That could be your car. And then it's squirting out over and over again as the time goes on.
Yeah.
So how fast was that camera? 600 frames a second, okay?
So pretty fast. But Sid, I mean, in this case, the thing just came out straight.
Came on the top, right.
And, the bottle couldn't go anywhere. So why don't we take the same idea but move it maybe to its side. Okay? So let me put the bottle right here. Let's see what happens.
No! It's still lit. Okay. Okay. So that was one thing that you could see with gases. Those are flammable gases, but we've got gas all around us.
Right, you're sitting in gas right
And
now.
you feel the air around you?
No, you don't feel anything?
Not really. How about
You
now?
feel it
Do
now?
you feel a little bit when we get this at
I
you?
think you can feel the air. Right? You can feel it? Okay, I see why, I see why.
Okay. So,
Well, let's see if we can show it to you. So what you just possibly felt, let's see what that looks like actually. So we put a little bit of smoke in here, and we do the same drum thing again, okay?
okay. 1, 2, 3. Oh, is that not?
Oops, sorry. All right.
Okay, so that was what you see with gases. Now we want to just do a little something with ordinary liquids. And so this is I guess a magical liquid because look, it just breaks a rod when it goes through there. See this rod, it's really a solid rod, but as soon as I stick it into this liquid, it looks like it separates. That it certainly changes the slope, and then or sometimes when you look at it in some angles, this thing actually looks like it's separated. So this is a magic liquid, but really it's not magic. All that's happening here is the fact that this is clear, air is clear, and the difference is that there's a difference, what we call index of refraction between them, which is how fast light travels in these two different media. And so what we just saw was something having to do with the fact that this thing had an index of refraction that was different between the two. But something else we could see with this idea that you have an index of refraction difference is if I take a sign like this, which
Wait a second, what does that
I don't know
say,
what
Sid?
this. I can't. Can you read this? I can't read this. Something's wrong with this sign.
Nag.
So what's wrong with this sign? Well, let's look at it through this medium. Okay, so can you see my face? So here I am. Okay, so now let's take a look at this through this medium. And so what does it do? Now you can read it because it's going in the right direction. It's going bang because this index of refraction is like a little lens which then reverses the horizontal direction of which direction is front and which direction is back. And so we were able to get here a reversal of this, so this liquid also acts like a lens. And so it really isn't magic.
But Sid, what else can it do?
Well, so now I want to show you that this thing really is magic. And so what I have here is a tube, glass tube, here. ordinary glass tube. I'm going to stick it into this container so that I don't hurt myself. And now I'm going to take this thing, I'm going to smash it.
Really?
I'm going to yeah. So can you verify that that is a smashed piece of glass, right? That is no longer a glass that I want to use. Okay, so I'm now going to take that and I'm going to pour it into this magic liquid and see what happens.
Well, that's really something.
Okay, so I get it all in there. And now what I want to see is whether I could get that magic liquid to, make that thing come whole again. Okay, so let's see if we can make that whole glass thing come back together into one nice tube. And so let's see what I can do.
Oh, I don't know.
Yeah, I don't know, but how about that?
Whoa!
How did that happen, huh? Well, the reason that happened was not because this is magic. We don't do magic here. This is all science, of course. And the idea about this is that index of refraction that I told you about before was between two clear objects, air and the liquid. But now what we did was we made the glass have the same index of refraction as the liquid. And so now one was inside the other and you couldn't see them. You couldn't tell one was different from the other. And so these two things, one is now invisible inside the other, and that was a principle of this, which is just a nice physics principle that is not magic, but still pretty neat. Okay, so there's something else we can do with the same liquid. So this is the same liquid. This is the liquid that we used here is glycerol. I'm going to use it again in this experiment. Glycerol, I don't know, does anyone know what glycerol is here? So glycerol is what you can do if you go to your drugstore. You can get bottles of glycerol that you then pour into liquids to, water to make bigger and better soap films, if you want to make big soap films. That's one place that you've seen it before. Another place that you may have seen it before is in McDonald's. I mean, McDonald's uses glycerol, or so I've been told, in their shakes to give it that je ne sais quoi de McDonald's. I mean, there's that special, wonderful, they call it body, we call it viscosity, but it's the same thing. Okay, so the idea here is that I have a container, transparent, it's a cylinder, and on the inside of this cylinder, I have a white cylinder that I'm able to twirl around here. So I'm just turning this inside cylinder around and around, and there's liquid between them. That's the same liquid, that glycerol that I have here.
So you can't see it.
And you can't see it, but what I'm doing is I do this, I'm mixing these things up, and you know that if you mix up a liquid, that's the end. You're never going to be able to get back to the original liquid again. Okay, so I do this, and now you can see that it's all mixed up, right?
Yeah.
No, because it was
clear. You
it was clear. You couldn't see it. So what I'm going to do is I'm going to put some dye in there so that we can see where the liquid is. And so you can see that there really is a liquid in here. And so I am going to put some dye here. I'm going to put it in the shape of an S. S for science, right? So we do science here, and so this is S for science, and I want to see whether, can I destroy science? And so I'm going to turn this up, and let's see what happens. Yikes, I guess I messed it up. I mean, this is the end of science. I mean, this is, it disappeared. Science disappeared on me. But there's physics with a bang, so maybe it was physics that was better than science. So let's try physics. So I'm going to try and put a P in here. Okay, so there's a P for physics. And now let's see whether physics is better, okay? So,
Uh-oh.
I guess it just, it got mixed up, and when it got mixed up, there's nothing else I can do, right? It's all gone. But and the power invested in me as a physicist, I'm going to try and reverse time. Okay, so I'm going to continue doing this. And let's see whether we can get these things to... Physics returned. Physics didn't disappear. Do you think science is still there?
I don't know.
Let's see if science is still there.
Oh.
So science and physics still stayed the same. And so this was not magic, even though it's the same liquid that I've been talking about. Again, this is just a simple theorem from fluid mechanics, which tells me that if I'm very careful about how I construct this and I use a viscous liquid, that was what was important about the glycerol, that it was viscous, big body. And so that is all that we need to have this thing be reversible. And so I am able to reverse time if I am very careful about reversing everything that I've done very, very carefully, and that's what this was constructed to do.
Right. So now, that was with liquids, right? Remember index of refraction and how material properties can change the index of refraction, so different materials have different indices, but sometimes even the same material can have a different behavior just if you change the temperature. And so now we're going to do that for a material that is kind of like a liquid, but it is actually a gas.
Okay, so for this, I'm going to need another volunteer. Anybody? Okay, you were the first hand up. Let's get this. Okay, so what I want, if you could come around this side, this would be great. And what's your name? Bradley? This is Bradley. Let's give her a hand. So thank you, Bradley. So what we want to do is we want to see if you're alive. And so what does that mean? That we want to see whether you're producing heat, right? Whether your body is working. And so what we have here is optics such that we are using this idea of this index of refraction that I just told you about to see whether heat is coming off of your body. So if I put my hand in here, you can see that there's heat. Let's see whether your hand is warmer than mine. So, oh, look at that. You are really alive. This person is really doing good, okay? So heat rises, and so you're seeing the plumes come off of your hand into the air, right? So this is what we're able to show with this simple optics demonstration. But let's see what else we could do. So let's take this and...
Right, and so because
this is not
heat changes the gas just a little bit,
okay.
Density.
So this is very, very cold stuff.
That.
And so now what we're seeing is that the cold stuff, cold air is falling, your hot air was rising, and so this cold air is dropping very rapidly in here. And so you can visualize that with this simple optics here. Okay? And so one last thing that we want to do is, we can also show this. So this is your, again, with a flame, you can see that the gas comes of the hot air from the flame rises, and you can see all those wonderful fluctuations around it. Okay, so one last thing that I'm going to try and do is to see if we can't raise this ball. Remember the Bernoulli effect that we told you about at the beginning? So if I put this in here, can you see that ball is floating? So you say it's floating. Okay, so now let's see if we can't see what's happening inside this. Okay. Okay. Okay, so what we're able to see, so let's give her a hand again.
All right.
Thank you very much.
All right, Sid. We talked about optics. We showed you something about the index of refraction. I think it is time to...
Put our lives on the line?
Exactly.
Put our lives on the line. Okay, so let's try this. So, what is this? A bowling ball, okay. And what is this? A nose. And which is harder, the bowling ball or the nose? Bowling ball is harder than the nose. Okay, so that's one of the things that we can all agree on, right? So what I want to do now is I want to show you that this thing will not hurt my nose. That's the idea here. Okay, so I'm going to take this bowling ball, and as I let this thing go across, I think it's a pendulum, it will come back to me. And what I want to show you is that this thing will never go above where it started, okay?
Very important.
So here I have an egg, and so this egg is, you should never hit this egg if it doesn't go below where it starts, okay? So here it comes.
Ooh.
Oh, well.
I have an idea. Remember the nose?
I guess I said so, huh?
Okay. Let's replace
So
the
let's
egg
replace
with
that
the
egg
nose.
with my nose and see what happens, okay? So here is my head cannot go any farther back.
Do you see that? All the way.
It's all the way back. And here is my nose, still there. And here is the bowling ball. And now I'm going to let it go.
Okay.
Ah! And so, what was it? I still believed in science, I still believed in physics, and it would not have come up above where I started it, except for the fact that I gave it a little push the first time. And that giving it that little push was enough to give it that extra energy, so it came back and smashed that egg. But I was very careful when my nose was in the way, I did not give it a push. I didn't let Heinrich anywhere near this thing to get it to go either.
Very true. So
that's that demonstrates this principle of conservation of energy. The energy of this thing cannot ever get any higher than where it started.
So what else can we conserve, Sid?
Well, you've got a bicycle wheel here.
On a chain.
On a chain. Well, that's kind of boring.
So we can make a pendulum.
Yeah,
okay.
That's kind of an ugly pendulum.
We saw that.
We saw that. Well, let's just hold it like this.
Oh.
That didn't.
Still a pendulum.
That doesn't help very much. Okay, so now let's do one thing where we
Turn this thing.
turn this thing.
Okay. Whoa.
And remember the first thing that Heinrich showed you with that slingshot? Well, that was a spinning object. Here's another case where we have a spinning object, and spin really makes things behave in a very strange and funny way.
Yeah,
And
so this is another conservation, but now we call that spinning momentum, angular momentum, and it keeps this thing from flipping over.
Right? And so this is something that you've seen lots of times on your bicycles. If you ever tried to wiggle your wheel while it was spinning, you see that there's some resistance to that, and that's what this is showing you. So that was conservation of energy, conservation of angular momentum. Now Heinrich is really going to put his life on the line with conservation of momentum.
Okay, so is this one of our more quiet experiments here? If you know what I mean.
Okay, so you're going to need to put your hands in your, because this will be somewhat loud.
Actually, you know what?
Oh, yeah.
I better take my jacket off for this one.
Okay.
It works better that way.
Okay, so Heinrich is getting ready. He's got his hard hat on. He's got his ear plugs on. Okay, so now he's going to let this thing go. What's going to happen? A lot of noise. Okay.
Okay, so what do I have here? Gas bottle.
And over in there, you may get a little windy.
You, sir. Ready?
Oh my God. We're going to have to take Heinrich to the hospital. So, could you take over the show now? Okay.
Okay, well, I guess we're in charge now. Cool. Hi. So what are we gonna do now that Heinrich's in the hospital?
Well, let's have a look at this table. What was next?
Well, I see a bunch of magnets.
Oh, I like magnets.
Yeah, me too. Maybe we can talk a little bit about magnets and electricity.
Yes.
So, what do we have here?
Oh, look, a coil.
Cool. What is this? It's a copper wire with a light bulb. That's not very useful. The light bulb needs electricity to run, and there's no battery, so this can't possibly work. But what else do I have here? I have a very strong magnet. So, what happens if I move the magnet really fast through the copper wire? I'm not touching the copper wire, I'm just pushing it through, and the light bulb is lighting up. This is because this is actually because magnetism and electricity are two of the same thing. So when I moved the magnet very fast, that made a moving magnetic field, and then that made current flow in the wires, and that made the light bulb go flash. What else can we do with moving magnets, Severine?
Look, there's a copper tube here. So, in principle, what you just did, if I move a magnet inside this copper tube, I can also create an electrical current in this, right?
Yeah.
So if I hold it while you throw the magnet, I should get an electrical shock?
Probably, right.
Okay, let's try.
Yeah. Well, the copper pipe's not magnetic, so I guess nothing will happen. You'll just get a nice shock.
Yeah.
All right. Are you ready?
Yeah.
Good.
I feel nothing.
Where did it go? Did it disappear?
It's in here. What's going on? Oh, I know. So, the same way a varying magnetic field can generate an electrical current, actually an electrical current also generates a magnetic field. And in that case, this magnetic field opposes the phenomena which created it. So in that case, the magnetic field created by this current swirling around the tube, we call also Foucault current, is inducing a magnetic field pointing up and pushing back the magnet. But that current isn't strong enough to push the magnet strong enough to make it stop. It's just slowing down its fall. So if we had a better conductor, we could generate a stronger magnetic field.
Yeah, maybe then it would stop.
What's better than copper as a conductor?
A superconductor.
Oh!
So, we happen to have some handy superconductors right here. So, so this is actually liquid nitrogen. It's very, very cold. It's minus 200 degrees, which is fast enough to freeze most things very quickly. But when you cool very special materials down inside liquid nitrogen, they become superconducting, which means that they're so good at conducting that they have no resistance, so currents can flow forever. Over here, I have another very strong magnet, and I'm going to try and make the superconductor float over the magnet. And there you go. But this is kind of a small magnet. It's kind of boring. What if I have a really big magnet like this one over here? I also have a big superconductor to match. Well, I can make this float over the magnet as well. And it runs around like a train. I can even put a piece of paper over the magnet, and it still floats. Maybe, oh, we have a rubber duck. I wonder if it wants to sit on the magnet. Maybe, or maybe Einstein? Oh,
Oh, it's warming up. Einstein is warmer
All
than
right.
the duck. So, what's really remarkable about superconductors is the state of the matter which is responsible of all these effects, and no resistivity, for example, are actually quantum phenomena. And so we can see a quantum behavior at our scale, and it's not only reserved to like the invisible small atom scales. And what happened in this material is very interesting, because when it's at room temperature, the electrons are not conducting. They just like, you can imagine them as like randomly running people just bumping into each other. But below a certain temperature, all of a sudden, it's as if everybody was holding hand, and so all the electrons are in a collective state. So for those who are familiar, it's called the Bose-Einstein condensate. And for those who are not familiar with that big name, it is actually a state where all the electrons are going to flow collectively, as if they were one single thing. And so this way they can flow through this material with absolutely zero resistivity. But what's also interesting is this material is not just creating supercurrents when it's exposed to a magnetic field. It also does something different. So it's not just pushing back magnetic fields, because it can do that too. So if it was only pushing back magnetic field, would that work? No. So superconductors can also attract magnetic field. They can also trap. So certain kind of them do it. And so this is one of many very interesting behavior that we can see in these materials. Okay. I think that's it.
oh, look who's back.
Oh! And you okay? You talking?
Anything for science.
Well, let's thank you so much for helping us.
Well, Sid, what do you say? I think we.
I'm kind of beat. I mean, can we have some relaxing music?
Let's have some music here. Let's have some music.
Very good. That's nice. Very relaxing.
Something here. I don't know what's that cable. Oh.
Oh, I broke it, Heinrich. I pulled too hard. Oh, wait a minute. Look at that. Well, I wonder, could we do this to a lot of people?
Okay, let's try that. Let's see. We need a chain of people here to help us with that. And let me come up here. No, we're coming to a certain
Let's
row.
see.
And maybe this row right
Maybe
here.
this row. Okay.
Okay.
So we're going to hold this.
I hold
and
this
we need
end
all of
the
you to
wire.
hold
I
hands.
touch you now. And
Whoop.
all right. Okay. Where's the end?
Here's the end.
Now hold on. You touch here. Ah. Well, that was fun, wasn't it? So that was a little bit of electricity, and now we need a little bit more electricity, don't you think?
Okay, so what did that do? That was showing you that you were a line of conductor.
Right, so your skin actually does conduct a little bit.
And that's why you should never get into the bath with an electronic object, because you will have the current going right through you, and that would not be good.
Absolutely not. All right, but Sid, if we don't use much current, but maybe a little bit more voltage.
Okay, well, let's see what that would do.
All right, so we have here.
I have a light bulb here. Let me just show you that I have nothing up my sleeve. Okay? But I'm holding a light bulb in my hand, no connections here or here. And what I'm going to try and do is light this light bulb with this Van de Graaff generator.
So this just makes a lot of electricity. And let's turn this on.
So just holding this close, I'm able to light up this light bulb.
Lightsaber.
May the force be with you.
All right. Well, if this thing can light up a light bulb just in your hand, let's see what it can do to Sid. He'll change a little bit. You'll see in a second.
Okay. So I'm going to try to get on here and see what it feels like to be a highly charged object.
Yes.
Okay.
Are you ready?
I am ready, Heinrich. Can you beam me up?
Oh, let's see what we can do here. Okay, here we go.
And so some of you may have noticed that I took off all my glasses and microphone and so forth when I came up here, because once I did this in class and I had glasses on, and I started getting shocks between my glasses and my eyeballs. And that was very scary. And I never wanted to do that again. So I remembered very carefully never to have that on when I come up here.
They said your hair is so nice. I think a little bit changed from what we just had before, right? All right.
So do you like the hairstyle?
I like it. Let me change it just ever so slightly.
Oh! I feel a little bit different.
You should. So what we just did is we charged up Sid to some couple 100,000 volts. Don't try this at home. Very high voltage, very, very little current. And now we're going to do the opposite. If you want, we use a lot of current, and we'll try to use that current to cut a can in half. So this is a soda can, empty. And it is in here in this coil. And now the idea is to run a lot of current through that coil so that it will generate a magnetic field. You just heard about magnetic fields and currents. And in fact, we want to make that field so incredibly strong that it will just crush that can and break it. All right.
So how much voltage are you going to put on here, Heinrich?
Well, all right. So we will do this now once the camera is set up.
You will then want to be able to put your fingers in your ears.
Okay, so we have here a huge capacitor that we're charging up to a very high voltage. Let's just wait for our camera. All right, so what we're going to do is we are hitting the button now, and it is charging up. It is at 1,000 volts, 2,000 volts.
Who wants 2,000?
3,000, anyone?
3, 4.
Who wants 4,000? 4, you got 4,000. Anybody more? 5? Good, you got
okay.
5. 6. How much? 6,000. Okay, I'll give you 8,500. 8,500 volts. 8,500 volts. All right, now, are you ready? Okay, now we're going to push the button here. 3, 2, 1. And
Whoa. And now you can see what how. This is one hot can, and you can see what it did to this can. It just squeezed it and ripped it apart. Well, it's pretty sharp. It's kind of sharp.
yeah, here's the other one. You can hold that. Anybody wants to see this? Be careful, it's sharp, right? So don't hurt yourself. It cut that all the way through. Now, what we're going to do is we're going to play this back for you, right? Because that was so fast, you probably didn't see, I didn't see what happened, really. Are we ready to play this back? All right. Can we make it bigger? There you go. Here's the can. Did you notice that little flash of light at the very beginning? That was from that discharge of the capacitor.
And that was 8,500 volts. And what comes out of your electric outlet is only 100 volts or so. So this is a lot more voltage than you would get from here.
And much more current. So this is a very, very cool experiment. But Sid, I feel under a lot of pressure.
I feel a lot of pressure too. Do you feel a lot of pressure? Has this been a very difficult time? A lot of pressure?
No pressure?
No pressure, okay, but do you feel pressure around you? I mean, are you feeling that things are getting to you?
I'm under
A lot of pressure. I'm not 15 pounds per square inch.
Square inch per pounds per square inch, right?
Well, I don't believe that, Heinrich. Otherwise, why are you still there? I mean, you should have collapsed.
There's some pressure also on the inside, and it balances.
Oh, that balances.
Yep,
That's
thank
cool.
goodness.
Okay.
So what if we make this an imbalance?
Yeah, then what would happen?
What if I have a situation where I take all the air out from the inside and just have all the pressure you are under right now on the outside?
I mean, so if I blow out,
Yes, that's it.
I should collapse. Okay.
And you would. But let's try that with this steel drum here.
Oh, that's a big steel drum. That's not going to do anything.
No, look at this, reinforced also, right? Right here. Has these ribs. It's not meant to do this really, but it seems strong enough, right?
That's strong. That's one strong drum.
All right, let's just take all the air out. What do you say? There's a pump here. There's a hose. It'll take some air out. Well, you see something happens. But it's probably pretty good, right? Let's see if something really good happens. Let's see.
I guess not. Well, Heinrich.
Uh-oh. Well,
Let's go on to the next thing. What do you think?
really? There was a lot of air in there, right?
Yeah, but
It's a strong drum, too.
it's a strong drum.
But it's a lot of pressure.
A lot of pressure, a lot of air.
Strong drum. Whoa.
Okay, so that's what happens. Just to the air pressure from outside is able to put enough force on this big drum for that thing just to collapse. Okay, and so that's,
So that's the pressure you're all under.
and this now became from a drum to an art object. Okay.
All right, so now I got a ping pong ball here, Sid.
Now that's a ping pong ball.
Do you all see the ping pong ball? All right.
Okay, can a ping pong ball puncture a piece of paper? No, let's see, so try
Okay.
it. It didn't do much. Try it again, Heinrich. Not much. Well,
What else can it do?
well, I don't know, but maybe, do you think that you could really make that ping pong ball go fast enough that it would not only puncture a sheet of paper, but how about puncturing a soda can?
That would be really hard, wouldn't it? But if I now used a cannon, could I get into or through metal with the ping pong ball?
So what we want to do is get that ping pong ball inside this can. Are we going to be able to do that?
All right.
Okay, so let's try. So we're going to put this one can there. So if we can go through one can,
Yeah.
should we try two cans? We want to try two cans. Okay, so here's the second can. Let's see what we can do with the second can. Two cans. Okay, is that enough? No, okay, so we should try three cans. Three cans? No? Okay, well, let's put the third can in there anyway. And how about four cans?
Really?
Okay, so we will put a fourth can in here. And just for good measure, a fifth can.
Yeah.
Okay, so these are all
All right,
tapped
so
down.
now what we're going to do, we will launch this ping pong ball through this tube. So Andrew's putting the ping pong ball in here, right? And now we're going to do this trick that we just showed you with that big metal can. But except we won't collapse anything.
This is very tough.
This is tough enough and it has a smaller diameter, but we have, at the end, we have some foil here and here. And if we evacuate now the middle, this tube, and I puncture the foil, the air will rush in and you get essentially this effect, and it will accelerate that ball. And let's see what it does.
So all the way down from there through this end.
Yep.
What's on the end?
There's another piece of foil.
Little piece of foil. That's supposed to keep all that air out.
Okay, so let's get our headphones here.
Okay, so again, this will be loud.
All right, we're using a pump to get all the air out of here. I can measure the vacuum. Well,
It's still pumping down, huh?
let's get all the air out of here. So the only thing that keeps the air out right now is a little bit of foil at the end. There and there. And I have a scissors here, and I can puncture one end, and the air will rush in and push that ball. All right,
Okay.
are you ready?
So be ready. Get your hands in your ears.
Okay. Camera ready? 3, 2, 1.
Okay. So let's see. Did it go through any of these cans? So let's see about this first one. Well, it kind of obliterated this first one.
Think about
Gone
that.
right through that one.
A ping pong ball. Just a little ping pong ball.
How about the second one? Well, that's completely gone. How about this third one? Well, this one got completely smushed. And this fourth one, it didn't get in, but it certainly tore this thing apart. And number 5 was just fine. Okay, so we were able to go through 3.5 cans, and we told you we wanted to get this ping pong ball in them. We didn't say for how long, and so they came in for a very short period of time.
Okay, but that was something you want to see in slow motion, don't you? Are we ready? Okay, so let me turn this light down. And here we are. See the ping pong ball go right through. Isn't that something? A simple ping pong ball.
Okay, so I don't know about you, Heinrich, but it's been a long show. I'm getting hot, and I'm getting kind of thirsty. Are you thirsty?
Of course.
Okay, so what should we have to drink?
How about some liquid nitrogen?
Liquid nitrogen? Oh, my goodness. Well, that's going to be pretty cold. We wanted a cool drink, so let's try a cool drink. And so you're going to put some liquid nitrogen into this soda bottle. Okay, so is that enough? No, okay, so let's put some more in. They want more.
They want more? Okay.
They want more. Okay. More, okay.
More? Okay.
More? Just a tiny bit more.
Tiny bit? Okay. Tiny bit.
Okay, so,
Perfect.
well, I actually think that's probably enough for right now. Okay, so let's try that.
Now
Oh.
look, this is really cold, right?
This is very cold,
And now we're going to put it in warm water.
and so I'm going to put the cap on this. I'm going to dunk it in the warm water, and then I'm going to run. Heinrich is going to be here, and he's going to try and put this over the top. But I'm out of here,
Okay.
just so you know. Okay, so here it goes.
And you are behind the screen, okay?
Whoop.
Let's see what happens.
Whoa! They wanted to do.
Oh, we have it on camera, so sorry. We need to play this back for you because that was too good. Oh, you want to see what happened here. Whoa. Was that cool or what?
Okay, so just before finishing up, we'd like to thank the various people who really made this whole show happen. And so there are a number of people. So there's an open house after this show is over, and the tours start at 12:30, and then again another one at 3:25, right outside this lecture hall.
Because if you go behind here, you know, as you go out, line up for some tours, see us scientists in our natural habitat next door. That's really cool.
Or go to Demo Alley. Okay, and so the open house was done by Sarah King, Justin Jureller, Eileen Sheu, Jeffrey Gustafson, and Maria, Cynthia, Vanessa, and Karina Jimenez. So
right.
We want to thank them. Our demo rep was Andrew Nadlman. Where is he now?
Andrew,
Andrew.
come out. Andrew, we need you.
Andrew.
Okay.
And there's Andrew.
There he is. Ah.
And Kevin Van de Bogart. Kevin, where are you? There's Kevin. Okay, thank you. Our high-speed camera operators, Severine Atis and Melody Lim. Our photographer, Savannah Gowen. All of the audiovisual crew who has made this possible to have this streamlined and streamed, and so that's Stephen Bandyk, Warren Friedl, Chris Kielch, Fredy Peralta, and Colin Hudler. And then we have to tell you that it takes a lot of people to make this thing work, and so there are about 90 volunteers who have helped make this work, and so we want to thank all of them. And we got funding from the Physics Department, James Franck Institute, our Materials Research Center, the Vice President for Research and National Labs, and the Dean of the Physical Sciences Division.
Okay, and with that, we would like to bid you a proper farewell.
Can you put these down? Just the blackboards. Yeah.
Ah.
Yeah, good. Okay, so this is the end of our.
Excuse me?
Oh, you'd like some gloves?
Oh,
okay.
I need some gloves.
Okay, and so this is, you may get been in the splash zone. Are you aware that you're in the splash zone for
You will notice this.
this? Okay,
You might want to move out.
okay. So we are thankful for all of you for coming to enjoy the show. We hope we will see you again next year. And until then,
Goodbye.
1,
2,
2,
3.
3.
Wow. So going out and
And enjoy the rest of the day. Thank you for coming.